Hey guys, this is Mr. Hart here, and in this Livescribe I want to just go through one of the example problems for derivatives. This is one of the first slides, one of the first examples in the 2.7 slides. Okay, so we're given this equation that describes the motion of a particle, x of t equals 1/3 t cubed minus 3t squared plus 5t plus 1. And we're just trying to find out these two things about it. We want to find the times the particle is motionless, and we want to know what the particle's acceleration is at those times. Okay, got some grammar there. There we go. Okay, so first thing, as you've probably learned in calculus already, if we want to find when the particle is motionless, in other words, we want to find when the velocity is 0. Okay, so before we do anything, let's find the velocity by deriving, okay, with respect to time, the equation above. So if we have 1/3 t cubed, that's going to become just t squared. Minus 3t squared is going to be minus 6t. Then plus 5t is just going to become 5, and then the plus 1 is going to go away. Okay, so we end up with this for our velocity. Now, if we're trying to find when it's 0, then we're going to say, okay, well, we know velocity is 0 on the left side, and then solve the stuff on the right. Now, just going back to simple algebra, we can factor this, okay, into two parts. We can say we have t minus 5 and t minus 1. Okay, two things that times to give you 5 and add to give you negative 6. Okay, and so that means if we're trying to say this is equal to 0, then we know that t in this case must either be positive 5 to make the first thing 0, or positive 1 to make the second thing 0. Okay, and that's always in seconds unless otherwise stated. Okay, so 1 or 5 seconds. So there we go, that's when the particle is motionless. Now, if we're trying to figure out the particle's acceleration at those times, we need to derive again and get the acceleration with respect to time. Let's box this off to let us know we're done with the first part. So acceleration with respect to time is just the time derivative of the velocity. So that's going to give us 2t for the first part. T squared goes to 2t. And then minus 6t just becomes minus 6. And plus 5 goes away. So now we're just going to plug in those two times we just got. So a of 1, okay, we're just going to substitute in 1 for t. Gives us 2 times 1 minus 6, which will give us minus 4 meters per second squared. That's our first answer. And then a of 5 gives us 2 times 5 minus 6, which gives us 10 minus 6, which gives us positive 4 meters per second squared. Okay? And there we go. So you can see by taking derivatives, we can just get some simple results about the time it took, or when it's motionless. We can figure out the accelerations. We can find the position, velocity, and acceleration at any time just by plugging the numbers into the different equations. Okay? And then last of all, just to give you kind of a graphical view of what's going on, this most likely, if we're thinking about the motion, if this is position versus time, a lot of these graphs kind of look like this. They'll start by going up, then they'll come back down, and then they'll go up again like this. And this is the first time it's motionless, so this would be like 1, t equals 1 in our example. And then they'll go back up, and this would be like t equals 5 in this example. Okay, so we're looking at a lot of these t cubed graphs are going to have this behavior. Okay, so just kind of give you a feel of what's happening. We can't really show direction changes in just the regular kinematic equations, which is why we have to be able to use derivatives and more complex equations to represent these types of motions. Okay, but that is it, and thank you for listening.